especially about quantum holography. So the idea basically is that I'd like to show you in a couple of experiments and some calculations how it is that you can use interference to measure the phase of a wave function. And so in a sense, we call it quantum holography, or I'd like to maybe call it wave function interferometry. And the idea is that you have something like an object wave function that you want to measure, and you have a reference wave function with which you interfere it. And so in order to sort of go over that idea, I'm going to talk about spectral interferometry, basically optical interference, and make a direct analogy of interference between light wave packets to then interference between matter waves in an atom or molecule. And I'm going to give a specific example where we do this in atoms. And I'm going to talk about a few experiments that have been done with molecules, and maybe mention a couple of other approaches, in particular tomography. And finally, I will end by talking about whether it matters. So how does the phase of a wave function matter? And I'll go over one specific situation where you can see a direct consequence, like whether a bond breaks or not, depending on the phase of a wave function. So let's start with just interference between optical pulses. And this is a well-known device that you are familiar with. It's a Michelson interferometer. And if we take pulses from an ultra-fast laser system, just a short laser pulse, and we go onto a beam splitter, then they can go both ways. Pulses are split. There's a mirror here and a mirror here on the delay stage. And so we can vary the time delay between the two output pulses here, and we can go to a detector. Now, if I vary the time delay between the two pulses when they're not overlapped, I don't see any interference, right? The electric fields have to be at the same place or same time in order to see any interference. So I can vary this delay, but once these pulses are not delayed with any overlap, then I won't see any interference. Unless, that is, I make a measurement which is spectrally resolved. What does that mean? Well, I simply go into a spectrometer. So if I take my two time-separated pulses, and I go off a diffraction grating and onto a position-sensitive detector here, then I get interference between those two pulses in the frequency domain. And now the interference fringes that I see here are separated by 1 over the pulse delay. So you can see that I can recover the interference by making essentially a Fourier transform. And the spacing between the fringes here is just this delay. You might say, well, how is it? I mean, didn't I just make this argument that I don't see any interference unless the pulses are overlapped? So what's going on? Well, in a sense, the spectrometer is providing that delay for us, because in going off the grating, each of the frequency components of this pulse gets stretched into a very long pulse, which is have the duration 1 over the resolution power of the spectrometer. So basically, if I have a spectrometer which spreads each of the colors out with a very fine frequency resolution, that corresponds to a very, very long pulse in the spectrometer, much longer than the delay between the two pulses. So then I get interference again at each position here where I have my detector. So that's just another hand-waving argument for why I do see the interference. And so this is going to be sort of the basis of a lot of the measurements that I'm going to talk about. So what becomes more interesting is if the pulses are not identical. So what I was talking about just a moment ago was the interference between two identical pulses, and you saw interference fringes which were regularly spaced, and they were spaced by 1 over the time delay between the pulses. But of course, we'd like to make measurements of something more interesting than just an unshaped pulse. And so let's say that we put some pulse shaper in here, and Phil Buxbaum described to you how you can use spatial light modulators and Fourier planes of pulse shaping devices to provide some pulse shape on one of these two pulses, and then the interferogram changes here. Notice that this is different. Keep reaching for the computer because I'm not used to this. Okay, so you see that the spacing between the fringes here is regular, and then it becomes irregular here as I put some sort of shape on my pulse. And so I have this irregular fringe spacing here, and what I'd like to do is I'd like to use that fringe pattern here to recover the phase of the unknown or the shaped pulse. Okay? If I represent my field in the frequency domain as in terms of an amplitude and a phase, it looks sort of dim to me. Can we turn off the front fluorescent light? or do I have control over that? This is maybe a little too dark.
This is verleider. Yeah.
Is that good?
Yeah.
Okay, great. So, so you see that I can write it as an amplitude and a phase, and then my total frequency-dependent interference pattern is.
Tom?
Yeah.
The mic's not working. So.
Oh, yeah. There's a red light now.
Oh. It's the battery. Why don't you take it off and put new battery in?
Okay. And there's some sort of resonance that we're doing with the lights here.
Okay, I have only one battery. I'll get a couple of batteries.
I don't think it's that. Something in the back here.
Ah, there we go. Did I get it? It's not buzzing. All right. Well, if I shout like this, can you guys hear me? Yeah. Okay. So I'll just shout for a bit. Yeah. Okay. Great.
Are there only two pulses you are considering?
Yeah, just two pulses. So this may be pulses from in a train from an ultrafast laser system, but the delay of the two pulses, let's say, is much, much, much smaller than the delay between pulses in the train.
How do you control it to make there to be only two pulses?
You can do lots of tricks to control that there's only two pulses. There are lots of devices that can be used for fast switching, and one is called a optical cell, and it makes use of the Pockels effect to rotate polarization of a laser pulse very rapidly. So if I have pulses coming from an ultrafast laser system, which typically in a titanium sapphire laser would come out at, let's say, 100 megahertz. So every 10 nanoseconds I have a pulse, I can use a very fast switch to just basically block off everything except one pulse from that train. And yeah, it's a nanosecond switching device, and that allows me to then isolate one pulse, and then I can go to my microsun interferometer and generate the pulse pair. And what I always thought was very cool is that just by doing, if you have a train of ultrafast laser pulses, that of course means that in the frequency domain you have a comb of frequencies, just like I think June you talked to you about. But when you go through something like a Pockels cell, and you just have one pulse, then you know that you must have a continuous spectrum. And so the act of that rapid switching, one pulse out of that train, basically fills in all of the gaps in the spectrum of that ultrafast pulse. So at any rate, so I'm going to always be talking as if we had a continuous spectrum and an isolated pulse, but if you have a repetition rate of a kilohertz, then you know that you actually have these cones underneath. So, we're going to do the battery. Okay. Okay, thanks. Okay, so you see that the point is that the interferogram here contains the frequency difference between the two pulses, right? So you have the amplitude of the one squared, the amplitude of the second squared, and then you have a term which is just the usual interference term. And all I'm doing is this interference in the frequency domain, because I'm assuming that I have a spectrally resolved measurement. And you can see that the measurement goes as the frequency difference between the two pulses. So if one of those pulses has a well-defined phase as a function of frequency, then that difference just allows me to measure the unknown pulse. And this is called spectrophotometry. It's a well-known technique used to characterize short laser pulses. And all you need to know is how to characterize a reference pulse. Great. Thanks a lot. Okay. So now I'm going to try and not shout anymore.
If you use the formula for the E omega,
all I'm doing is I'm taking the sum of the two fields.
Yeah, whereas it's omega tau.
I'm sorry. The omega tau is just basically the delay between the two pulses. So that was, if you go back up here, that's this tau. Okay? And that you know this from the Fourier shift theory, basically, that a shift in one domain corresponds to a linear phase in the other domain. So that omega tau just comes from the pulse delay. So now, you know that you can invert this spectrogram to recover the phase difference between the two pulses. And you can see that by basically just rearranging things in the former equation. And you see that if I rearrange, I can basically just solve for the cosine of the phase difference, and then you can extract this phase. And so there's some sort of beautiful solutions to the technical problem of taking an arc cosine, and I'm more than happy to discuss that with anybody or say a few words about it now. But there are tricks to get around the fact that that it's not well defined to take an arc cosine. Okay, so we're going to basically do the exact same thing we just talked about, but now with wave functions inside a single atom. Now we're going to work with an ensemble of atoms, but basically the interference is taking place in each atom individually. So I'm going to talk as if I had a single atom, even though the experimental measurements are made in an ensemble of atoms in order to avoid having to repeat the measurement lots and lots of times. So the idea is basically completely analogous. I'm going to take a laser, and I'm going to go into a Michelson interferometer. I'm going to generate two pulses. One of them is going to go through a pulse shaper, which is going to allow me to change the time, basically the electric field distribution for our shaped pulse. That's going to generate a shaped wave packet in the ensemble of atoms. And then we're going to interfere that shaped wave packet with an unshaped wave packet generated by the unshaped pulse from the Michelson interferometer. So these two pulses are now sent into a vacuum chamber, and we'll discuss exactly what's inside the vacuum chamber and how that works in a moment. But the experiment is essentially analogous. I'm just taking my spectrometer, which used to be here, and replacing it with an atomic measurement. Okay? And what I'm going to do is I'm going to make a similar measurement where I'm going to take my object wave function and my reference wave function, which are just created by the shaped laser pulse and the unshaped laser pulse, and I'm going to project those onto the eigenstates of the atomic Hamiltonian. This is my spectrally resolved measurement. So, just to say that again, for the optical measurements, I use spectrally resolved interference to measure the optical phase. Here I'm going to use, for my wave function measurement, spectrally resolved interference to measure the wave function phase. And the reference is a wave function that's generated by an unshaped laser pulse. And we can characterize that wave function with other techniques, which I'm not going to go into in great detail, but we're going to basically generate a localized wave function where all the phases of the eigenstates that are constituting the wave function are going to be roughly zero. And so it's sort of like an unshaped laser pulse. It's the analog of that. Does that answer the question? Or?
Yeah, except that I don't see how to characterize it.
You don't say how to do what?
I don't know how to characterize it.
I'm sorry.
How do you characterize it?
Oh, how do you characterize it? Well, there are, you can use ionization as a function of time delay to show that the wave function must have been localized near the core of the atom to make sure that it's really what you think it was. Also, calculation helps you to do that. So there's a bunch of ways that you can infer that the wave function was the minimum spread in position, and that minimum spread in position wave function must be an unshaped wave function. Similar to the idea that if you take a short laser pulse and find that it's the minimum duration with the available bandwidth, then you know that the phase of the frequency components that are used to generate that short pulse must have been zero, or relatively zero. So what's this wave function? What is it? How do we make it, and what is it? So the idea is that we're going to use, we're going to try and make a coherent superposition of principal quantum states of atomic cesium. And the idea is that if I take a short laser pulse and I start from the 7s, which is not the ground state of cesium, but we've gotten to this state via some other tricks. Actually, we've gotten to this state by 2-photon absorption from a dye laser, which is exactly what I talked about a couple of days ago, that you can calculate the 2-photon absorption rate. That's just a preparation of this state from which we can launch our wave packet. But this was sort of the, some small part of the motivation for discussing how you can actually calculate multi-photon absorption rate. But from this state then, we're going to launch an electronic wave packet by shining a short laser pulse whose bandwidth spans several eigenstates of the atomic Hamiltonian. What that means is that I'm going to make a transition, I'm going to make a dipole transition from this state to this state, and 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 this state at the same time, because I've got bandwidth to do that. So all I'm doing is I'm exciting a small portion of this wave function up to a superposition of states up here. And the reason I call that a coherent superposition is because when I do that with a short laser pulse rather than a light bulb, there's a well-defined phase relationship between these states, which is defined by the phase relationship between the frequency components that make that short pulse. Yeah?
What determines the higher cutoff in the N number?
Oh, essentially the bandwidth and how I tune this laser pulse. So you know that the states converge here as you go through the continuum. And so I could pack in lots and lots and lots of states if I tune this a little bit higher up, right? And I could get an infinite number of states in that wave packet. But I wouldn't be able to resolve them, and you'll see that that's an important part of making a measurement. So we've tuned this conveniently so that it can excite sort of on the order of 10 states, which is an interesting wave function. But if we tuned it too much higher, we might excite 100 states, but we wouldn't be able to resolve them and be able to make that projection onto the eigenstates and uniquely identify how much probability for each eigenstate. So that's what stops us from. Yeah?
I'm sorry. I still not getting how you can excite a wave function that's by all over the states.
Aha. Okay, so imagine that I take a narrowband laser and I tune it from this state to this state. So this diagram is sort of a Grotrian diagram where I'm assuming that these are all the S states, which I'm ignoring up here. Then in this column here are, let's say, all the P states. So which are the dipole allowed transitions. And let's say that this is n equals 28, so principal number 28, L equals to 1. And I can make a transition, and I'm ignoring fine and hyperfine structure here because the time for spin-orbit coupling to evolve is much longer than the time scales for this experiment. And so I can basically ignore it, and I'm treating L and M sub L as if they were good quantum numbers. So imagine that I take a laser and I tune it from this guy to this guy. Right? Then you can see how I can excite n equals 28p just by tuning the laser between these two guys. Right? It's a transition dipole, and I can use Fermi's golden rule to calculate what the excitation probability is. Now imagine that I take another dye laser and I tune it to the n equals, or another diode laser from n equals 7 to n equals 29. And let's say I take another laser and tune it from n equals 7 to n equals 30. That's right, yeah, so I'm getting there. So now imagine I take all those diode lasers, or those narrowband lasers, and I find some way to lock their phase. Okay, so I can measure their phase, I beat them against each other, and I lock all their phase. That's exactly what an ultrafast laser pulse is. So it's basically taking all of these modes of a single laser and locking their phase. And that's equivalent to having lots and lots of narrowband lasers whose phase I'm locking, but I'm doing it all with a single laser, so it makes it technologically much, much, much easier. And that's also, in a sense, what makes an ultrafast laser powerful, because you can do multiple different things in parallel. So now I've got this wave packet, which is a superposition of principal quantum number states here. And by coherent, what I mean is that I can write this superposition as just a sum. These phi sub n of r are basically just these eigenstates of the atomic Hamiltonian. They're the radial eigenfunctions, and of course they have some spherical harmonics multiplied by them. So r here is the generalized position coordinate. And so the idea is that these are functions of only space and not of time. They're eigenstates. And I'm exciting them with some probability, amplitude, a sub n, which is dictated by the laser pulse and the transition dipole moments. And I realize that, that maybe the bottoms of my slides are not visible. Should I maybe try and change the aspect ratio so that, no? Okay.
No, and actually I forgot to turn on the TV, so let me turn on the TV.
Oh, okay.
But it actually works from the back.
Okay.
And you can all stand up, right? It's good exercise.
So the point is that these a sub n's have an amplitude and a phase. And by coherent, I mean that that phase is well defined. I can make the same wave function if I just shone a light bulb onto the atoms. Okay? except that these phases would be completely random and have no meaning. I mean, they would have meaning, but they would just not be, they would not have any well-defined or predictable values. Okay, so the point is that the short laser pulse generates these amplitudes and these phases. And if I can measure those amplitudes and phases, then I can measure the complete wave function, right? Because all I then do is I take these known eigenstates, which I can either calculate or maybe measure in some other way. But let's say that we have a reasonable understanding of what the eigenstates are. Then all the measurement is basically just figuring out what the complex coefficients are for those eigenstates. Then this phase factor here is just telling you how the phases of the eigenstates evolves. That's what makes a wave packet, right? I don't know if people talked about wave packet evolution.
Not much. Did Phil talk about that? I don't remember.
Okay, so maybe a word or two about that is that...
People talked about them in the context of ionization and things like that.
Okay, yeah, I guess, Lou showed these beautiful movies of the... But in terms of, I guess, maybe you haven't heard about it discussed in terms of eigenstate superpositions. This basically just tells you where all the time domain evolution comes in quantum mechanics. It's basically if I can write any wave function expanded in terms of an orthonormal basis, and then it's just basically the phase evolution of each of the eigenstates that determines the time evolution of the wave function. It's just these eigenstates beating against each other. Just like it's all the different Fourier components in a short pulse that beat against each other that tell you how that process propagates. So, at any rate, you can see that the problem now comes down to measuring these complex coefficients. And what's actually happening in the atom is that by producing a superposition of eigenstates, you're localizing the electron, which I've cartoon diagrammed here. Here's the core, and here's this electron. And a Rydberg atom is nothing more than an atom which has a high principal quantum number. So it's basically sort of like this electron is kind of like a planet orbiting the sun. Okay, it's localized, and it's far away from the core, so it's very weakly bound, and that's all that Rydberg atom means. So we now have this electron, which is localized because I've added together lots of eigenstates that are going to cancel in most locations and add up constructively from some very small region in space. And I want to know what that wave function looks like by measuring each of these complex coefficients. So how do I measure these complex coefficients? Well, it's kind of nice to have been here this week and seen some sort of ideas get repeated in different contexts. And the idea is we're going to make use of an old trick called state-selective field ionization. And as Lou talked about earlier, the critical field for field ionization of a state with principal quantum number n goes something like this. What that means is that if I just take my atoms, which are, let's say, like this, and put them in between two parallel plates which form a capacitor, then I can just put on a modest field of a few hundred volts per centimeter and tilt the potential like this. This is nothing compared to the kinds of... So Lou showed you lots of pictures like this, right, where you have an electron tunneling out. And this is not that different at all, except that we're talking about Rydberg atoms, which are very, very weakly bound. So the fields that I have to put on are very, very modest by comparison. I don't have to put on an ultra-fast, strong field laser pulse. I can put on a field just by putting in, a couple hundred volts between two plates that are separated by a centimeter. And if I vary how that field looks like in time, then each of these eigenstates pop out at a unique time, right? Because they each have a separate field ionization threshold. So then if I just look at an oscilloscope, as I ramp up the field, this was one of the most beautiful things I ever saw when I walked into the lab the first time, that you just see the electrons just popping out like this, boom, 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 boom. And you can just right there look at the scope and say, oh, this is n equals 28, n equals 29, n equals 30, 31, 32, 33, 34, 35, boom, just like that. And so you've just effectively measured, you've taken the wave function, you've projected it onto the eigenbasis of the atom. Because each of the principal quantum numbers in that wave packet ionize at a unique field. And if you ramp the field in time, you get the populations just read out in time, the probabilities for being in those eigenstates. And so, that,
Excuse me.
yeah.
So, do you assume that the wave, the shape of the wave of the pulse does not change with time?
The amplitudes for being in each of those eigenstates doesn't change with time. As you see right here, this guy here is a complex number, but once the laser pulse has excited the wave function, the amplitude, A sub n, doesn't change its magnitude. There, of course, is spontaneous emission, but that happens on very long... Was that? Okay. So, of course, yeah, you're right on the money. There's spontaneous emission, but for a Rydberg state, because the transition dipole matrix element is so small, because of essentially wave function overlap, right? I mean, you've got this ground states or valence states which are very localized, and then you've got these Rydberg atom wave functions which are huge. And if you just take the transition dipole matrix element, well, there happens to be an R in between, but essentially it's a wave function overlap integral. That integral is very, very small, meaning that the spontaneous emission lifetime of these guys is about a microsecond, or several microseconds.
If you want to have some kind of localization there, you might probably need to, from what I think, you might need to include some continuum wave functions to get that going. So, but you have, I think, do we have any opportunity of measuring those?
Not with state selective field ionization, because you're measuring how deeply they're bound. So we don't localize the wave function to a delta function or anything. We localize it as best as we can when you have a basis of 8 eigenstates which we're exciting.
No.
So now here are the populations of each of the states. And that's essentially measuring your signal as a projection of your wave function here onto the eigenstates of the atomic Hamiltonian, E sub n, and square that. That gives me my A sub n's magnitude. Okay? So that's really nice because this is my atomic spectrometer, right? My atomic spectrometer is giving me a spectrally resolved measurement of the power, which is basically a spectrally resolved measurement of the probability for being in each of those eigenstates. But I don't have the phase which I need in order to reconstruct a wave function. So, going back to the same idea, we're going to use interference to get that phase. Right? So, we're going to go back to this idea that we have both the shaped wave function and a reference wave function, and the total wave function in each atom is going to be the sum of these two. And the reason that we can do this is because the 7s state that we start from, we can think about a reservoir of population or probability. We take some small fraction of the atom into these Rydberg states, okay? But we do it perturbatively. So there's only, let's say, 10% of the probability is in these Rydberg states, but there's still 90% in the 7s state down here. Now we can have a second pulse that can transfer a little bit more probability. And those two transfers can interfere. Those two wave functions, we've taken a little bit of wave function and put it up here, and then we take a little bit more wave function and put it up there. And those two wave functions can now interfere. And now we look at the state-resolved interference between those two wave functions, and we can get our phase out. And you see that right down here. If I can hit the right button. So, oh shit, no, I obviously couldn't. So now our total wave function, when we've excited two wave functions, I'm going to use A to represent the coefficients of the shaped wave function, and B is going to represent the coefficients of the unshaped or reference wave function. And so I've excited these two guys, and now I'm going to be interested in their coherent sum and projecting it onto the eigenstates n. And you can see that just as in the optical case, we recover the phase difference between the two wave packets for each eigenstate. So, in this particular experiment, there was a small problem, which is what led me to ask you and make the comments that I did yesterday, Lou, about the phase fluctuations. So it turns out, for technical reasons, but this is a sort of a repeated theme, which is why I even measure this point, that if the timing between the two pulses is not perfectly defined down to a fraction of an optical period, then on average, the phase between the two wave functions, you have to average over, let's say, several measurements. And then on average, the phase will completely average out to 0. Because if this time delay here is not defined well enough to within one optical period, this cosine function averages to 0. And then there's no interference at all in the total average measurement. So you might think that you're just totally screwed at this point, but actually you can use second-order coherence measurement to recover the phase information. And this is very much in analogy to the Hambry-Brown twist experiments. The basic idea is that I can construct a normalized correlation coefficient. And I think the easiest way to describe this, which I find very intuitive, is if you have phase instability or timing instability between the two pulses, then if I look at the signal in any eigenstate, okay, let's say this guy right here, from one laser pulse to the next laser pulse, from one shot or one measurement to the next, this is going to go up and down randomly, okay? Because the term, this tau here is varying on an optical period, which means that the interference term is going to go from maximum to minimum randomly, which is going to make this total signal randomly oscillate, okay? And so, if this, I don't know why I keep going back to the computer, I think I'm a slow learner. At any rate, if each of these randomly oscillates, you don't get any information out. But the point is that they're not going to randomly oscillate relative to each other. And so what you're interested in is each guy is going up and down, perhaps randomly. But how do the neighboring populations or probabilities oscillate? If they oscillate together in phase, then you know that the relative phase between those two eigenstates is 0. And if they oscillate out of phase, then the relative phase is pi. So the point is that while each state may randomly oscillate up and down, relative to the other states, there's a well-defined phase relationship. And that is not lost in the phase locking, in the lack of phase locking. So by constructing a correlation coefficient which measures how these oscillations are correlated with one another, you can recover the phase difference between the states. And that's exactly what this slide shows here. So if you construct this normalized correlation coefficient, which is basically just a covariance divided by variance, to normalize it, then you essentially recover this phase right here. So that's what we can do in the lab, is you can go and measure this normalized correlation coefficient. And so the measurement consisted of measuring that normalized correlation coefficient as we varied some phase that we applied on a pulse shaper to vary the phase of the shaped wave function. And you see beautiful sinusoidal oscillations here. There's lots of noise, which I won't go into the details of the technical source of that noise. But you can still see nice sinusoidal oscillations here as we apply a phase to the shaped wave function. So that tells you that this whole scheme is really working, that you're seeing interference between these two wave functions. And this is just an inset to show that actually if you go out even to a nanosecond in time delay between the two pulses, you still see good interference. And the reason that this was an interesting question is that there were lots of reasons that we suspected there might be decoherence in the measurement, a loss of phase information due to black body radiation or other sources of decoherence. And yet the coherence was maintained for many cycles. So the time scale for the wave packet evolution here is on the order of the energy separation between the states. And if I could fit 10 states or so into a, let's say, 100 femtosecond pulse, that gives you a rough idea that the time evolution for the wave function is on the order of 10 times 100 femtoseconds, or about a picosecond. And so yet we saw coherent oscillations out to nanoseconds. That's telling you that this is a very low decoherence rate, because the phase information is being maintained for thousands of oscillations. Okay, so here's the main result then. We can construct a table where we measured the phases and the amplitudes. The amplitudes just came from the heights of those peaks in the state selective field ionization. And the phases came as I described to you just now, with some error bars from some nonlinear least squares fitting routine. And now, voila, I can use those amplitudes and phases to reconstruct my Schrodinger wave function. This is showing you in atomic units as a function of x and z of the atom, what the amplitude is for being in, at a particular location in space. And it's a p state, and so you can see that there's a cosine dependence right here. And you can see that there's also some coloring to this graph, and that coloring is the phase of the wave function. So by measuring the energetically resolved or state resolved probabilities and phases of the wave functions that make this coherent superposition, I can therefore reconstruct the spatially dependent phase and amplitude of the wave function, because I know how each of the eigenstates depend on space. And these are all summarized in a PhD tutorial article from 2002 in Journal of Optics B. We can play this game to do feedback to reach a target wave function. Because not only do we have the ability to measure the wave function, we also have a pulse shaper. We have an ability to control the wave function. And so you might say, well, let's pick some target state, which we call here a dark soliton. And this actually consists of a wave function whose phases for the eigenstates go 0 pi, 0 pi, 0 pi, 0 pi. And this was our target wave function. And we said, well, let's see if with any random delay between our shaped pulse and our reference wave function, we can generate that target. So that is, make the pulse shaper shape the laser pulse so that it can generate our target wave function at any time. And this is, of course, not possible if you excite with this unshaped laser pulse. But you can tweak the phases in order to make sure that they all line up to the right value at some target time by shaping the laser pulse. And this just shows you that with some feedback, we can start with some random wave function here and still achieve the target in 2 iterations of the feedback. It should really be a single iteration because we understand how to do everything, but for technical reasons it took 2. Again, starting from another random wave function, we can go back to our target, and from a third random wave function we could hit the target. Just by shaping the laser pulse, measuring the shaped wave packet, feeding that back to the pulse shaper and telling it, no, the phases were wrong, you need to correct them, and then it could readjust them in this way. So, now that you have a complete measurement of the wave function, it's interesting to construct the Wigner distribution. Because you would like to look in phase space, what does the wave function look like, right? I mean, in a sense, let's look at this target wave function, or one of the wave functions that we measured. Well, you see, you can see that it's got some probability of being out here, somewhat localized, not totally localized. But I have no real idea which way it's moving, right? It's very hard to look at this and see which way the wave function is moving. And that's because your eye is very bad at doing the Fourier transform, right? The momentum of the wave function, which is what I'm talking about in terms of moving, is of course given by the momentum space wave function is just the Fourier transform of the position space wave function. But I can't do that in my head. And so just as Phil and others talked about the idea of looking at a time frequency distribution in order to understand what an ultrafast laser pulse that's shaped looks like, we can do the same thing constructing a Wigner function, which is something like a quasi-probability function. Quasi because it's not positive definite. Okay? But the Wigner function has some nice characteristics of features that its marginals are well defined. So if I integrate along momentum, I get the position space wave function squared, probability distribution in space. And if I integrate along spatial dimensions of the Wigner function, I get the marginal along momentum, which is just the momentum probability distribution. So now, unfortunately this was not the most fortunate choice of line colors and types. But anyway, now you see that here's 0 momentum down the center, right? And you can see that the wave function has slightly negative momentum, right? Because there's a larger probability here to the left of the vertical axis. And its position is at about 1,000 atomic units, 1,000 Bohr radii. And you see that that sort of makes sense. There's a big hump here at about 1,000. And you see lots of coherent ripples, which is the sign of a coherent wave function. And if I integrate over this with a small, or convolve this with a function that has an area h bar then I get essentially a real quasi-probability distribution, which is now positively definite, and that's called the Husini distribution. I'm not going to go into that in detail. For a nice comparison, you can see there's some black lines which I'm trying to trace out here. It's sort of like a vision test. And these black lines here represent the classically allowed regions in phase space. So anything outside of those black lines is classically forbidden, and anything inside is classically allowed. And that's just given by this equation here. Here's the angular momentum barrier, here's the Coulomb potential, and here's the momentum. And I just set this equal to the energy of the state for the lowest n state in the wave function and the highest n state in the wave function. So these are my classically allowed limits.
Is your Wigner function positive everywhere?
No, it's not. So I'm sorry that I didn't include a color bar, but they're opposite signs, the lighter and the darker blue here. I can also then look at what does the Wigner function look like when the electron is at its inner turning point nearest the core and furthest out, and you get this beautiful symmetric distribution here. When it's at its inner turning point, you can see that half the momentum is negative and large, and half the momentum is positive and large. Half the wave function is still moving in, half of it's moving out. On average, it cancels out, so it's at rest, but actually it has high and low momentum components. And at its outer turning point, you can see that it's localized out at large radius here, and the momentum is basically zero. This makes a lot of sense, right? I mean, at the inner turning point, well, it's turning around, but all of that energy, which was, because it's near the deeper part of the Coulomb potential, it has to have a lot of kinetic energy. Therefore, it has to have both high and low momentum. And you can see that, again, most of the probability lies within the classical boundaries. Okay, so a second example that I want to talk about is just sort of moving on from an atom to a molecule, because you might say, well, okay, this works all nicely for atoms, but maybe you're interested in something a little bit more complicated, like a molecule. And this similar kinds of ideas works for measuring the vibrational wave function of a molecule. What do I mean by that? Well, if you just consider a diatomic molecule, then you can generate a potential as a function of the position for the two nuclei. And that wave function that describes the probability of being at different internuclear separations is the vibrational wave function. And we can measure that wave function in a method that's analogous here. So, in a similar idea, we have Michelson interferometer that comes after a laser. One pulse goes through a pulse shaper, one pulse just goes through a variable delay bar. And we have a shaped and an unshaped pulse that is hitting an ensemble of molecules here. But the idea here is that it's very difficult with a molecule to measure a state-resolved probability of being in different vibrational eigenstates. For the Rydberg electrons, it's easy to talk to an electron directly, right? Because an electric field talks to that electron. It has a direct force on it, the Lorentz force. However, the nuclei in a molecule are both neutral. So you can't exert a direct force, and it's therefore more difficult to make direct measurements of the vibrational wave function of a molecule. So the idea here, which was proposed by Wolfgang Schleich and his collaborators about the same time that this original work on the Rydberg states was done, said, let's imagine that we excite a molecule from the ground, from the ground state up to an electronically excited state, and we'd like to measure what the vibrational wave function looks like there. Okay, and here they're interested in a specific Schrödinger cat state where the molecules' coherent superposition of being here and there. And so the idea was, can we use fluorescence from this electronically excited state to somehow give information about the vibrational wave function? And so basically, again, we just now say that we can make a shaped wave packet, which is our object. And again, it's the exact same kind of sum, except now the n index runs over vibrational quantum numbers. Okay, so n doesn't refer to different principal quantum numbers of the electronic wave function. It just refers to the vibrational states of like a simple harmonic oscillator. Okay. And now we come in with a reference pulse, which is delayed with some time tau. And again, the total wave function is given by a coherent superposition. If we were to resolve that wave packet in terms of the probability of being in a particular eigenstate n, that sum would look something like this. And again, it would have terms that go like interference terms here that depend on the complex coefficients a sub n and b sub n for the shaped and unshaped wave function. But of course, we can't measure those p sub n's for the reasons that I just outlined. It's very difficult to measure the vibrational eigenstate resolved probabilities for a molecule. So the idea was, can we look at the total fluorescence from the molecule as a function of the time delay between the two pulses? Does everybody know how, does anybody, who knows how Fourier transform spectroscopy works? Okay. Who doesn't know how Fourier transform spectroscopy works? Okay. Okay, so the idea is that if you want to make high-resolution spectroscopy in a region of the spectrum where it's difficult to have a spectrometer, then you can use a Michelson interferometer to measure the absorption or fluorescence or some signal as a function of the delay between two pulses. And if you do that for a very, very large range of delays between the two pulses, then you can achieve a very high spectral resolution just by looking at the time at the absorption or fluorescence as a function of time delay between these two excitation pulses. And this is basically just a simple statement that the Fourier transform of an autocorrelation function, which is what you're measuring, is the spectrum of that radiation or the spectrum of the absorption. So it's basically it's a simple mathematical idea that tells you that you can get spectral resolution by just looking at it at something as a function of delay between two pulses. And it's the same idea that comes about from this measurement here. So if I take two pulses and I excite some system, I get spectral modulations. So you see that there's information. If I go on and I shine this onto some absorber, and I do it for a range of delays, and I measure the absorption, I'm basically scanning out the fringes in the frequency domain. And so I'm making essentially a frequency resolved measurement without using a spectrometer. So that was sort of the motivation behind this measurement. That if we can measure the fluorescence as a function of the delay between two excitation pulses, then we can reconstruct the phases of the states of that vibrational wave packet. And this is just the formula that relates the total fluorescence probability to the probability of being in a total eigenstate n after the two pulses, which was given by the expression here. Okay? So you can see that the probability of being in eigenstate n depends on the interference of the two pulses, the two wave functions. F are the vibrational eigenstates of the ground state. Let's assume that the molecule starts off from an initial pure state that's in the ground state of the molecule. And so then F would just be 1 here. These are the vibrational eigenstates in the excited state potential. These are just the frequencies of the transitions from the ground state. And the point is that I don't want to go through the math here in detail, but I just want to motivate the idea that it's possible by making measurements for different phases between the excitation pulses to recover a signal which has the phases, the complex coefficients of my shaped and unshaped wave function in it. And then this signal here can be inverted to get the complex A and B values. And here's an example of a calculation where they calculated what the fluorescence looks like as a function of the delay between the two pulses. And you can see that it oscillates because as the two pulses are delayed, your total probability for exciting any particular eigenstate is going to oscillate up and down because as the delay between the two pulses varies, the spectral intensity at any given frequency will vary. And that spectral intensity is responsible for exciting some eigenstate in the excited state potential. So that's sort of a second example of how you can use interference to measure the phase of a wave function. You know, we went from an atom to a molecule, but both of those were bound states. And there was a question about continuum earlier, and so, in a sense, not that I was anticipating that question, but it nicely falls in, that we can now address what happens if we promote a wave function to the vibrational continuum here. Can we make some measurement of its phase via interference? So the experiment is a simple but beautiful experiment carried out by Henrik Stibelfeld and co-workers, and here's a reference down here. And I'm happy to provide all the references if you can't see it or copy it down. But the idea was that they took short laser pulses and they shone it on an iodine molecule at a frequency where they could go to a potential which is dissociative. So the molecule would just slowly break apart. And what they did is they had a pulse that would slowly make the molecule dissociate, it would start to dissociate, and then they had another pulse, just like all the other experiments we've talked about, which came and made the molecule dissociate again. So you have two portions, or two amplitudes for the molecule to dissociate, which were created at different points in time. And those two can interfere with each other in ways that we've talked about. Perhaps those don't spatially overlap, but again, if you make a spectrally resolved measurement, you can see the interference between those two wave functions. What does spectrally resolved mean in this case? Well, I think about the Fourier transform of position, and that is basically momentum. So if you can make a momentum space wave function measurement, or a velocity-dependent measurement, then you can recover the phase as we've talked about earlier. And this is exactly what they did. They used a technique that we talked about briefly earlier, velocity map imaging, to measure the wave function in velocity space or momentum space of the dissociating molecule, and they were able to look and see interference there. So the experiment is as I outlined. They have two pump pulses that go to this B state of iodine. Depending on where my photon ends up on this potential here, I'm either bound or dissociative. So if I were to excite down near the bottom of the well, obviously there's no dissociation. But if I excite up here, just above the barrier to dissociation, then I get two slowly dissociating wave functions which can ride out to the continuum, and that's shown here. And you can see that the wave functions are spatially separated. But of course, you know that if you take a free electron and you just put it in space, what does that electron do? If I take an electron and I localize it to a very small region of space, what does the electron do with time? It spreads, right? Why does it spread? Well, if I've localized it in position, it must have a range of momentum values, right? Just the uncertainty principle, which is basically just wave mechanics. And so, you know that if it's spreading out, its wave function is going to become delocalized. And a similar kind of thing happens here as these two wave functions are riding out in the potential, right? They have some spread of momentum components because they have a finite spread in position, right? So the momentum space wave function is just the Fourier transform of these guys. And if these are somewhat localized in space, they must have some spread of momentum components. So as these ride out on the potential, they're going to be riding out like my hands, except they're going to be spreading like this. And they're going to soon overlap. And so then you're going to get interference in both position and in momentum space. And what I think is particularly beautiful about this experiment is that they had a very clever way of measuring the wave function in both position space and momentum. That wasn't a question, was it?
No.
Okay. So, and the way that they did that is that they took a probe pulse and they ionized the molecule. And they can ionize it to either a repulsive Coulomb potential, which leads to iodine plus iodine plus. So this is basically just as if you had two positively charged particles. Of course, you get a repulsive Coulomb potential there. And this way, the position of the molecule got mapped to different energies here in this potential. And that means that they come out with different velocities far away. And since we're using a velocity map imaging, you're again transforming, and so you get a measurement of the position space wave function. It's a little bit confusing because you go position to velocity and velocity to position. But the other way that they could do it is they could just ionize it to this relatively flat potential, which just led to iodine neutral plus iodine plus. And then because they're using velocity map imaging, This gave them a measurement of the wave function as a function of velocity. So by projecting this wave function onto two different curves, which had two different characters, they're able to measure both the position dependence of the wave function and the momentum dependence of the wave function. So it's really cool. They had two different filters, or two different things, two different basis sets on which to project the wave function in order to resolve it and measure the interference. And so that's done by velocity map imaging, and just to remind you how that works, okay? You create your molecules in between a series of electrostatic fields which are generated on these plates here. And that produces basically an electrostatic lens which maps each velocity here to a unique position in space here. And so if I am traveling with a large transverse velocity, I get a large transverse position here. It's just like a lens, an optical lens. And then I can take a picture of this position-sensitive detector with a camera, and that camera image is then basically what I use to record that velocity map image. And so then they got a bunch of rings here, and of course you might, there's a detail which I haven't talked about in velocity map imaging, that you actually are creating a three-dimensional distribution, right? And you're projecting it onto two dimensions because your detector is a two-dimensional detector. And so it's sort of like taking a soft-boiled egg and taking that egg and smashing it into a wall, right? And what you really want is what the egg looked like, not what the splatter on the wall looks like, right? And so there's something called an inverse Abel transform that makes use of the fact that there's cylindrical symmetry to the problem that allows you to reconstruct a three-dimensional egg from the splatter on the wall. And so they can take this two-dimensional image here, which has lots of fuzz, and reconstruct it to make something which has much more detailed structure. And the idea is that you can imagine why this has a lot of fuzz, right? If you have some egg, right, and let's say that there are different layers in that egg, like the shell and the yolk and stuff. The shell, which had a very well-defined radial location, gets projected onto all radial positions when it gets splattered on the wall, right?
It doesn't have to get splattered.
Okay.
Think of an X-ray shadow.
Sure, there are ways of doing slicing as well. So I didn't talk about DC slicing, which are other, is that what you were thinking of?
No. I just think if you, suppose you were taking an X-ray photo of an egg, you would want to use the Abel transform to turn the plane image into the round egg.
Okay, yeah, so it's the same you would use the same reconstruction approach here, and I guess my analogy of splattering is perhaps not perfectly accurate, I guess, thanks. So in a sense, it's a projection of this egg onto the wall, and you want to use the inverse Abel transform to reconstruct. So once one does that reconstruction, then you see detailed ring structure here, and that I'll show you in a moment is the evidence of the interference. And what they point out is that the rings at close here for low radial values correspond to this velocity image, and at high radial values, those correspond to the position-dependent wave function. And that makes some sense because the position dependence we were saying we got from projecting to this repulsive potential here, and so you're going to get a lot of kinetic energy as you dissociate on this repulsive potential. That sends you to much higher position on the spatially resolved detector because it's much higher velocities. So, so here are the results, and what's really beautiful is that you see interference modulations in both in position. So what this is showing is that they're showing experiment and calculation, and it's showing it for different time delays, which are perhaps not very clear here. This is at 5.9 picoseconds, 7.9 picoseconds, and 9.9 picoseconds. This is for the pump probe delay. So this is probing the wave function at further and further distances from the R equals 0. And what's really nice is that the red and the black curves are what happened if they changed the delay between the two pump pulses by only 1/2 optical cycle. And what you expect to see there is you expect to see a bright fringe go to a dark fringe, and a dark fringe go to a bright fringe. And that's exactly what you see if you look at these graphs here, that the interference fringes shift by exactly pi because they've just changed the phase of the two wave functions relative to one another. And you also see interference in velocity space. And both experiment and theory show you those same interference wiggles. Now, this experiment used two identical Planck pulses. So they were not able to reconstruct the wave function because they didn't have a shape in an object or an object in a reference wave function. But they could have done that in principle just as we did for all the other experiments. And of course, you can look at the Wigner distribution for this wave function, and you can see that if I project onto the x-axis, I get my position-dependent probability amplitude, or probability distribution rather. And if I project onto the y-axis, I get my velocity-dependent probability.
There's a question there.
Yeah?
I will ask a general question. For these interference experiments to work, does the excitation need to be very weak? Much smaller than a pi pulse?
Exactly right, yeah, because if you've put all of the population into the excited state with the first pulse, there's nothing left to promote with the second pulse. So it has both a fundamental, and then there's a practical issue too, that in the weak field limit, you can use perturbation theory to calculate what the wave function should look like. In the strong field case, you would have to do a more detailed calculation. But yeah, you need to have some wave function left over because that your reservoir is sort of the ground state where you can, the interference is in each atom or molecule separately. And so you can't interfere neighboring atoms and molecules, and therefore you need to have more population to put up from the ground state. That's right. So it's always a very small fraction of the population which we're exciting up there.
And how many atoms are you using?
Well, in the Rydberg Wave packet experiments that I talked about, probably on the order of thousands to million. So I don't know that we ever did any specific counting there, but it was many. And it's simply just, do I want to repeat the measurement a million times, or just do it on a million atoms? But the separation between atoms, it was a very dilute beam nevertheless. So that you could really think about them as individual atoms because their interatomic separation was much, much, much larger than the spacing, than the size of the wave function. So, well, yeah, okay. I'll just say one word about how there are, of course, other ways to measure wave functions. And I'll give a very brief, sort of just passing reference to other approaches, such as tomography. And this is an example of orbital tomography, which was pursued by many groups around the world now, originally performed by the group of Paul Corkum at NRC, but I believe there are similar measurements going on in Lulu Morrow's lab and other labs around the world. Where the idea is basically not to use interference explicitly, but to make use of projections of the wave function in order to measure it. And so this was the idea that they wanted to use orbital tomography to measure the highest occupied molecular orbital in a nitrogen atom, in a nitrogen molecule. And so if you consider the molecule as a cartoon diagram here, and if you take an electron in a strong field, as Lou described earlier, and rip it away and recollide it 1/2 cycle later, then you can generate high harmonic radiation. And the high harmonic radiation is proportional to a recombination matrix element squared, and that recombination matrix element involves the continuum wave function here, the dipole operator, and the orbital or wave function that you're interested in measuring. And so the idea is that if you can align the molecules, which we won't talk about how you do, but you can use a non-resonant laser field to align the molecules, a strong field laser pulse to align them, and you can change that alignment angle, then you can measure how this recolliding plane wave projects on to different angles or different different alignments of the molecule, and you're essentially making slices of or projections of this guy here onto this wave function. So essentially, they can do that both angle resolved and spectrally resolved, i.e. as a function of different frequencies or K vectors for that returning electron, by measuring different harmonic orders, so different frequencies of light, as a function of different angles between the molecule and the laser field that drives the electron away and recollides it. And by taking these measurements, they could reconstruct this highest occupied molecular orbital. It's actually not the highest occupied molecular orbital because this is a multi-electron molecule. And so they're actually measuring something more akin to what's called a Dyson orbital, which I won't go into in detail here. But it's basically a projection of the n-electron wave function onto the ionized n-1 electron wave function, which in this case looks a lot like the highest occupied molecular orbital. So that's maybe some technical details, but the point is that you can measure the amplitude and the phase of that highest occupied molecular orbital, and the comparison with calculation is reasonably good.
Is this for the N2 molecule?
This is N2. So, the last few minutes of the talk, I want to just basically say, well, okay, you can measure the phase of a wave function, but does it really matter, right? So I want to just show you an explicit example that we made a measurement in my lab, where we showed that, yeah, it can matter explicitly, and it can matter on sort of a consequential scale of, do I break a bond in a molecule or not? And whether I break the bond or not can depend on what the phase of the wave function is. And that's what this next couple slides is meant to show. So, we take a molecule. In the case here, it's probably a lot uglier molecule than you'd ever like to consider. It's, this guy right here, which is a halogenated methane molecule, but I won't refer to it again, so you can just pretend that it's a diatomic if you like. The point is that we can take this molecule from a ground state, or from a launch state, as I'll refer to it here, and excite it to a ground state in a three-level system where the wave packet oscillates. So this is essentially a pump-dump experiment. Phil talked about those earlier this week. And it's a special pump-dump experiment where the wave function evolves in some coordinate here, which is, let's say, a bending of this angle. Okay? And then there's another coordinate along which the molecule dissociates. Okay? And if I raise it to this excited state here, the molecule can come out of the screen and dissociate. So there's two different coordinates that are at play here. And the point is that the wave function that's evolving on this state here can cross a resonance location twice per oscillation period. Okay? And what I'm going to try and point out to you is that when it's going this way and when it's coming back the other way, the only difference between the wave function at the same location is its spatially dependent phase. Well, the only difference between it classically is the momentum, right? Because you think, well, it's going one way and then one time and the other way the other time as it passes back and forth. And how we describe that quantum mechanically is spatially varying phase. That's the momentum. So what I'm going to show you is that here's a calculation carried out by Tomasz Varmi at the Hungarian Academy of Sciences. And he calculated what the position and time-dependent wave function looks like for that molecule in the ground state. And you can see that the wave function starts out off at high bending angle, goes into low, turns around, and comes back out. And it crosses this point labeled by a dashed line, which was this location in the cartoon, where you can resonantly excite it to this dissociative state with a propulse. Okay? And naively, in thinking about first-order perturbation theory, you'd say, look, how does the probability to go from this state to this state depend on the wave function at this location? Well, and so you'd think, well, okay, first-order time-dependent perturbation theory, I would imagine that depends on the amplitude of the wave function here, multiplied by some transition dipole moment, and multiplied by the strength of the field, right? So actually, it shouldn't really care at all whether the wave function is going this way or that way. It doesn't know anything about the momentum or the phase of the wave function, and it shouldn't matter. And so, if you actually look, so this is a calculation, and you say, let's do it for weak fields, so somewhere down here. The x-axis here is the field strength of our probe field, and the left axis here is the probability for the population transfer and dissociation. And if you look for a left-going and a right-going wave function, for weak probe fields, you can see it doesn't make a difference, as one would expect naively based on perturbation theory. However, as I crank the field up, you see something very interesting start to happen. And that is, at very high probe fields, there's actually no probability for population transfer if you're going to the left, and 100% probability or approaching that if you're going to the right. That is, the phase of the wave function differs for these two, the spatially varying phase, but that's it otherwise. And that's shown in this cartoon. Here's the probability as a function of position for the wave function going to the left and the right. And they're exactly the same. We didn't get the timing exactly right, but these overlap reasonably well. And the differences between these two probability amplitudes is not the reason for the difference that I'm going to show you, that I was showing you. Here is experiment and here is calculation, and they're different for lots of different technical reasons, which I don't want to go into. But one can show that they actually are in reasonable agreement, despite the fact that they don't look exactly like that. But you know, it's kind of funny, right? Because what this is saying is that, hey, I'm shining a strong field on resonance to the molecule, and yet it's completely transparent to that. And the reason it's transparent is because of the phase of the wave function. Because if I take the same wave function and just change the spatially varying phase, it absorbs and has 100% probability of dissociation.
Do you know if the calculations were done in von Oppenheimer approximation, or?
We'll get to that in a moment. I mean, essentially, I will address that question in the next slide.
So what are the dotted lines on the right-hand curve?
So this is for left going, and they're for two different. So the wave function goes back and forth and back and forth, and the dotted and the solid lines are just for the first time you're going to the left, and then the second time, just to show that there's not significant dispersion of the wave function as it oscillates back and forth. And so, obviously, it's not the amplitude of the wave function that's differing here, but it's the phase. And how do we do a calculation that shows it? And so here is a sort of a two-level cartoon. We're pumping the wave function up here, and then it comes into resonance, and then we can probe it. And there was a sort of a light bulb which went on when it said, when we realized that, oh, this depends on the intensity of the probe field. So that tells you, oh, if you're doing a strong field experiment, maybe you should really look at the dress states. So if you just take these Born-Oppenheimer potentials here and calculate the evolution of the wave function, assuming that there's a perturbative effect, it doesn't capture the dynamics. You have to consider the fact that, as I talked about last time, the strong field of the laser changes the energies of these states. And it changes the energies of these states in a position-dependent manner. And so what we have to do is we have to take this two-level Hamiltonian for the ground and the excited state, which just has dipole coupling between the ground state and the excited state. Here, this is just the dipole. This is the Rabi frequency. And we're going to look at the dress states where we take the excited state minus a photon energy in the ground state as our two diagonal terms. And if we diagonalize that Hamiltonian and look at what it looks like, then you get something like this. If there were no coupling, you would have a real crossing here between the potentials. However, as I turn on my coupling with different probe field strengths, you can see that you develop an avoided crossing. And now these dress state potentials give us a perfect way to describe what's going on. Because if the wave function approaches from the left, going to the right, And if it does so in a slow way, that is, if we can make this avoided crossing large, so that the Landau-Zener hopping probability, as I talked about last time, is low. Don't want to go on video. Okay, anyway. So then you can imagine the wave function rides down this adiabatic potential, and it goes right through the avoided crossing, but notice that the character of the state that it's on changes in going through the avoided crossing. So it goes from the ground state to the excited state perfectly smoothly with 100% probability. On the other hand, if it approaches from the other side, i.e. with the opposite spatially varying phase, then it sees a barrier, turns around, and goes back on the same potential that it came in on, i.e. 0% probability of dissociation. So this model beautifully captured the dynamics that we saw and make it explicitly clear that the dissociation depends on the strong laser field dressing the potentials, and it depends on the spatially varying phase of the wave function. This is not the only example, this is just a simple example that I knew from my own research that shows you that the spatially varying phase, or the phase of a wave function, can matter, not just its probability amplitude. So in summary, I hope to have convinced you that we can measure the phase of a wave function, and we can do that using interference. There are, of course, other ways to do this, but interference is a powerful way to do this because it allows you to think about separating out into eigenstates and measuring then the eigenstate resolved interference pattern. So it's a very simple and to my mind, intuitive way of measuring things that makes use of spectral resolution and interference. And it basically relies on a direct analogy to optics. And the phase of the wave function can really matter. And once again, I just would like to thank the people who were responsible for a lot of these, for funding these experiments, collaborations which we've had, and people who carried out the work. This was some of the work of Sarah Nichols, her thesis work. Earlier work I talked about was Carlos Traero, and there are many other students in the group who have contributed as well, and Maria as well, who's here. So thanks a lot for your attention, for sticking around to the last day, and I'm more than happy to answer any further questions that people might have. Yeah.
So what's the holography result there?
Well, so the holography was a simply, I mean, the original theory paper that came out, which is given in this one, in this example here, was this paper.